back into this. Okay. Recording. Okay, recording is on. All right. And somebody's static in the background. Someone else can mute themselves. All right. So today, to start with, one other thing that's not in our snow model, the SnowX field experiment in 2017 was on Grand Mesa, Colorado, and it's snowmobile heaven. And so we ended up just measuring millions of snowmobile tracks. And so Matthew Sturm is one more thing we're not modeling, sent pictures of his old and his new snowmobile. And I think the red one is the new one, it looks shinier. And he wanted us to tell him what are 5 things that are different between these 2 snowmobiles and how do they affect the snow and how do they affect the snow differently. It's not your homework, but if you're curious and you send Matthew an answer, he will let you know if you're right or wrong. I do not know the right answer. All right, so schedule. We are getting down to the final leg of our month. Today's the 22nd. Critique of reading 2 is due. Homework 2 is due on Wednesday. If people would like me to push that back to Friday, let me know. If you would rather have it due so you get it over with and then can work on your presentation before Friday, then I'll leave it due Wednesday for now. But if enough people ask me for a reprieve, I can move it back. I am switching the order just in the interest of homework. Everybody says we got 2 votes for Friday. All right, homework 2 I will move to Friday on the Canvas. You can have till Friday. For today, I'm going to switch the order and talk about evaluation first because I think evaluation came up as part of your homework 1. There were some questions. I'm not going to grade anybody down on it, but I feel like we haven't talked about how do you know even what is a good snow model. It's not trivial. And then on Wednesday, I will talk about distributing a snow model across a watershed. We will not actually be distributing any snow models in this class. You can see that point snow modeling is enough work for 1 month. But I will talk about that because I know that's where a lot of people are going, but I'm going to save it until Wednesday. Okay, so thank you everyone for doing homework 1. I know it ended up being a bit more work than I initially anticipated, but I think our results are very exciting. I wanted to plot the results more than prepare all my lectures. So just a recap, where were we? Here is Reynolds Mountain East in Idaho. We were simulating snow at this lovely site that's sheltered because it has some trees in southwest Idaho. And we did 4 layering schemes. We had the Jordan scheme, which got up to 100 different snow layers. We had the basic CLM scheme, which had 5 snow layers. And then we had 2 versions of the CLM scheme with a thin and a thick surface layer. And so, the first thing is, okay, so we ran all the model runs. Everyone successfully managed to get the model to run, which we all learned is no trivial task in its first place. So the model ran, we got all our output. So plotting data is a skill that takes a lot of practice. So what were people's initial thoughts after homework 1 about plotting? How do you make graphs of your data? Any take-home messages after finishing homework 1? Just use Xarray. Xarray is the best thing ever. Any other thoughts? Everybody likes Xarray. And any other thoughts beyond Xarray? Loops are good. It's a lot of thoughts about just the logistics of how you make plots. How about the information content of plots? You have to use Xarray and you make this beautiful plot. How do you interpret it? Matplot library or matplotlib is also useful. It's hard to know which variables are relevant. That's a really good observation. Yeah, where do you start? What should you plot? If someone doesn't tell you what to plot, how do you know? How do you work your way through it? So I'm going to, observational data would be helpful. Yeah, if you just have 4 model runs and no one told you what truth is, how do you know which of all these 4 model runs are truth? How do we assess that? So I'll show you a little bit of just my thought process as I go through plotting, and with the caveat that I have not learned X-ray, so I outported everything to MATLAB because I know how to plot in MATLAB. And so, it's a learning curve, all different aspects. And being able to make an informative plot is not trivial. It's beyond the time we have for this class, but I would, recommending if you have time to, spend time on learning data visualization. So the first plotting tip is always plot something that you're pretty sure you know the answer to. And always plot that first, and mainly because, as you probably learned, it was actually easy to mislabel or misname something just when copying and pasting in the Python script. And you may have output one model run and labeled it another model run. And then after you're putting things in matrices to plot, you may grab the wrong one. So one thing I was most sure of on this experiment is that how many layers there should be, right? So I made just a plot of by 4 years number of layers, and Jordan definitely got up to 100, CLM got up to 5, and then thin and thick both got up to 2. So I was happy that I at least had them labeled correctly and they were what you think you are. You'd be surprised how frequently you can get them all mixed up. The next thing is you plot the entire run duration to make sure that it all looks like snow, right? It all accumulated in the winter and melted in the spring. But the next thing is you look at this and it's, it's not very informative for process representation. What, at this scale, I can't even tell if one melted earlier or not. I can probably say that, when you zoom out to this level, they aren't that different, right? You could probably pick any number of layers of models and it gives you roughly a decent snowpack. So I could assess that, but assessing more from looking at a plot of all 4 years is pretty hard. So one thing I typically do is I look at 1 year at a time so you can zoom in and actually see differences. Okay, so if I go in to 1 year at a time, and these are some of the things I asked you to plot. So here's just each by water year. The first thing I noted was in the 2 largest years with the most layers, the Jordan scheme accumulated less snow than all the rest. So why is that? Why does having more layers end up with less snow? Any thoughts? There was some early melt, more heat flux, more rapid heating, a quicker response to heat. So actually, when you look in 2000 in the spring, it's actually melting a little bit slower in the spring, right? It ended up accumulating less. It's melting slower later. Even in 2002, right? It ends up disappearing later than the thin snowpack. It actually seems in the spring to be better in the early period. Yeah, it's melting more in the early period. So it's the only one that really gets mid-season melt. Absolutely. So let's look at some more plots. The surface temperature the scale doesn't look too different, right? Jordan looks kind of in the middle of the rest. And the density for 2000 isn't very different. The other thing I noticed, which many of you noticed as well, is that in most of the years, 3 out of 4, the density during melt was lower in the 2-layer runs, right? So the density was quite a bit less during the melt season. My hypothesis was there was less liquid water retained in the snowpack, that more layers allowed more liquid water retention and therefore a more water per unit depth of the snowpack, or a higher density. Many of you zoomed in, and when you zoomed in, you can actually see like what difference. It turns out that the 2-layer thin melted earlier, and the 2-layer thick melted later, but the difference was about 5 days. Again, depending on your application, may not be critically important. Zooming into the melt season, you can see this difference in density a bit more. If you zoomed into a diurnal cycle, you could see that the 2-layer thin cooled the most rapidly. The 2-layer thick cooled the most slowly. Many people noted that in their homework. I thought it was interesting that the thick one spent the most time with the surface temperature near 0 degrees C, but it also was the slowest one to melt out. So, number of hours spent at 0 degrees C doesn't necessarily mean you melt faster, right? The one that was melting the fastest actually had the surface temperature that got the coldest at night. Was interesting. Here's just another picture zooming into a different period, again showing that the 2-layer thin cooled the quickest and the 2-layer thick cooled the slowest. And in these were some winter runs that also, in this case, the thicker one took more time to warm up. All right, so I think these were kind of the basic plots that I asked most people to get. So, okay, you've run your model, you've made your plots. Now what do you do? Does it mean any, what should you do with your results? So the first thing is, it's a really good idea to take a moment to think about why you did these runs in the first place. You may be done. For the assignment, you were done, right? In your world, you did your runs, turn in your assignment, go on to the next thing on your to-do list. If your goal was to get a reasonable estimate of snow water equivalent at Reynolds Creek, a 5-day difference in meltout timing isn't a really big difference. So probably a 2-layer model is fine. And most of the modeling run done at Reynolds Creek has been done with a 2-layer snow model. If your goal is to use your model to estimate density, for example, you might have a depth measurement of snow from lidar or photogrammetry. Then the density with the 2-layer model during the melt season was quite a bit different, which could cause a 10% or greater error in using the model for density. So you might want to look into a 5-layer model. If your goal is to explain how snow models work and you're obsessed with this, or you're teaching a class on the subject, right, then you probably want to make some more plots because you just keep asking why, right? And as you guys can all tell, I probably fall into this last category, so I made some more plots. So the next thing after plotting the state variables, right, you have an idea of, what's snow water equivalent, what's the surface temperature, what's the density. I like to look at what are the fluxes of water and energy out of the snowpack. So again, similar to before, this is just one of the water years, 2003. And I've plotted here sublimation, sensible heat flux, and drainage out of the bottom of the snowpack. So how helpful are these plots? Your votes? Good, bad, otherwise? Can't see you, so you have to type something or unmute yourself and make noise. Yeah, you need to zoom in, right? You plot this, you're like, okay, well, it looks like scribbly lines, right? It actually does look remarkably like my 3-year-old coloring. So the next thing, even though I zoomed into a year, for something that varies as rapidly as the heat flux and the drainage, it's hard to know. You can see, there are a couple midwinter melt events that are having drainage, but it's confusing. So you need to zoom in. Multiple people said that. How do you know where to zoom in? So the strategy I tend to take is I like to replot. So take these same plots, but now plot them as cumulative sums over the water year. So now, again, water year 2003, this is cumulative sublimation over the whole year, cumulative sensible heat flux, and then cumulative drainage out of the bottom of the snowpack. And when you do that, you actually say, okay, this 2-layer thick model is actually has different fluxes than the rest. Sensible heat flux, despite the fact that those diurnal cycles in temperature were different, added up over the whole year wasn't that different, but the sublimation and the drainage were different, and they seem to diverge right in December. Something happened in December, and maybe even in November, that looked, really different for that 2-layer with a thick top. So what's that? And this is more example of just how you do detective work with your model output than that, this is the most important event for you to understand. But let's see, there's something in December that happened with our 2-layer thick scheme. So take that from the cumulative plot and zoom in. So now if we zoom in to the actual fluxes at that time, you can see that there was a fair bit of sensible heat flux. So there were a couple of fairly warm days on, December 14th and 16th here. And during those days, it was warm. The snow was sublimating off everything except for the thick layer, right? So there was a fair bit of sublimation going on. And there was also melts out the bottom of all of the snowpacks except for the 2-layer thick one. So what happened with the 2-layer thick one, right? It did something different. Any ideas? We had no snow to start with. Nothing was happening because there was no snow. That was actually my first guess. That the whole thick layer had to reach 0, so it just was too hard to warm it up. So this is what's actually really interesting, and I have to go back to Bart and Martin about this. So when I looked in and wanted to know like what happened, it turns out that even though there's no drainage out the bottom, there's no sublimation out of the top, that the snow surface temperature decided to get warmer than 0 degrees. So the energy actually went into warming this thick surface layer above 0 degrees and not into melt or sublimation. Back to the last slide. How does cumulative sublimation increase and decrease? Yeah, I can go back. Okay, so cumulative sublimation. So basically, what you see on the plot on the upper right is sublimation, right? So sublimation, so basically we are defining down as a positive flux, right? So drainage down out the bottom of the snowpack is a positive number. So when we lose snow out the bottom, we have a positive number. Sublimation is going out the top, so it's going in a negative direction. So water that is sublimating away to the atmosphere is a negative number here. So this is negative, and so sublimation that is negative, we're just adding this up. And if we have a lot of negative numbers, it just keeps going down, down, down. And so we see a net over our entire season, we tend to lose water from the snowpack to the atmosphere. Now we could get, you can see here, we actually have some points here where sublimation is positive. What does that mean? That actually means that water is condensing on the surface of the snowpack. So you actually have mass from water vapor in the atmosphere condensing on the snowpack, and that is basically increasing your cumulative sublimation. If that doesn't make sense, ask another question. And so our heat flux, you can see, is always our heat flux is defined as, positive down towards the snow. So we're putting energy towards the snow. So it's always positive, and you can see our cumulative sensible heat flux, which is just adding up all of these numbers, and this time series goes up the whole time. All right. Why the surface temperature goes above zero, I have no idea. I also can't figure out how the snow water equivalent decreased slightly, but the water did not go out via sublimation at the top or drainage in the bottom. So if anyone has any ideas, let me know. At this point, I'm kind of stumped about what the model did here. But is it a problem with the model? It's a good question. I am going to ask. I think it could be a problem with the model, and it could be that most models do not make a super thick surface layer in a 2-layer model. Most try to make it fairly thin. And so it could be we've created a numerical instability. Is water pooling on the top of the snow? Maybe. Yeah. Even though I think the snow water equivalent is supposed to include water. And why it wouldn't drain anywhere and just sit there. And then I really don't know. We'll keep looking into this and we'll report back if I figure it out. And if anyone else has any ideas, let me know. It's December 2014, 2002. You can see if it's in your runs too, or if it was just an instability that happened in my run. I don't know. Okay. So then the other sort of surprising thing, we could look at snow depth. Yes, just once you zoom in enough, we can start actually asking process studies, and we can start getting ideas of more things to plot, and then we're limited more by our time. Okay, so I asked this question before, why does having more layers lead to less total snow? And Joran said that there's some winter melt. So again, we can do our cumulative plots, which help give us an idea of fluxes. And as Joran pointed out, it's in the drainage, right? That for this year, and this we're showing 2002, the sublimation wasn't that different. There's probably less sublimation out of the Jordan model than the other models. And so it's occurring as drainage and not as sublimation. The heat flux is pretty much identical. So any more thoughts about why? Why does our multi-layer model melt kind of throughout December, January, where nothing else does? So multiple layers create thinner layers that can melt easier. So a thinner layer might be easier to warm up to zero. Okay, so here let's look again. Let's zoom in. It happened in December. Again, sublimation, aside from the 2-layer thick model, not sublimating at times, pretty similar across everything. There's melt coming out the bottom of this snowpack, and only the Jordan one, not the rest, at a time when the snow surface temperature is pretty cold. So here on the 25th, we're definitely not getting anywhere near 0 degrees C at the surface. The surface is getting down to negative 30 C at times. And yet we're getting some melting out the bottom. So I don't think it, is a time response as water moves through all layers, maybe the temperature gradient. Looks like the snow ground interface was about 0 all year. Maybe hydraulic conductivity conducts drainage more efficiently. Something with a temperature gradient. So here is, this is from Justin's plotting code, which I borrowed and then realized that I didn't have enough time to figure out how to fix the color scheme so it did much other than 0. But I know that I'm showing this gold color at times when there is liquid water in the snowpack. So from this plot, water years 2000 and 2002, and these are kind of a contour plot of where the liquid water is with snow depth. we're the ones with less total snow in the Jordan scheme. So what do you see? And the timestamp's also a little messed up. So forgive that this is still with snow depth is right. And think of the yellow as being when there's liquid water present. So what do you see happening here in the water years and it with less total snow? Yeah, the liquid water is present at the snow-soil interface. So what's actually happening is that this is the only one of the models. If we go back to, hold on a second. Picture that all of them, the 5-layer scheme really worked on resolving the gradient near the surface, but the only one that had a thin layer near the bottom is the Jordan scheme. So if you had snowfall over a warm soil that was just slightly warm, not super hot soil, but a soil that's slightly above zero, the ground heat flux has a potential to cause melt in this 100-layer snow scheme, but does not have the potential to cause melt in any of the other ones. So it's actually melting from below. So if that's our hypothesis, let's go back to where we are here. Okay. Our hypothesis is that there's something happening with heat flux at the bottom. What might we plot next to check that? We could look at soil water flux. We could look at flux at each layer. If I think the soil is heating the snow, how could I test that? What would I want to look at? Ground heat flux. What might be even temperature in each layer, including temperature in the soil layers. And Justin's code was very, net heat flux at the bottom snow layer, temperature in each layer. So Justin's code was very nice in that it got down to the snow, but he got rid of the soil because thought we didn't want to look at it. So we might actually want to look at that soil again after all, and might want to look, and again, the dates are a bit off, might want to look at what was the soil temperature before that first snowfall event and about what's happening through the winter. The other thing, just from Justin's plots, and I zoomed in on the 2-layer thick and the 2-layer thin model for this year, just in between these two peaks here, is that it's actually complicated how the temperature evolves with these different layer schemes. And so it's not always intuitive exactly, which layer stays colder longer. So here's the thick one, and you can see it's actually, staying, the lower layer stays colder longer with the thicker one on top. Because the cold days only cool down the top one. Or, why it happens, I think, would take more time. Any questions on homework 1? I may not know the answer yet, but any questions before we move on to more general thoughts on both homework 2 and on model evaluation?
Hey, Jessica, quick question.
And thank you for
why. Yeah, it's easier. Why is snow density unitless?
Why is snow density unitless?
Because so in the formula you gave us in the homework, it's what, SWE divided by snow depth. Or no, you gave it to us the opposite, actually.
Did I give it to you backward?
It was reversed, yeah, but in your MATLAB code, you reversed it to the right way, so I just went with that. But I would still expect the units to be kilograms per meters cubed, no?
Yes, so you can, So basically what I'm plotting, you can plot density as kilograms per meter cubed, or you can plot it. So basically see how I have SWE, my units say millimeters or kilograms per meter squared.
Mm-hmm.
So if you do SWE as kilograms
Oh,
per meter squared, and then you divide it by meter, you get density in kilograms per meter cubed, which should be something from like 200 to 400 on this plot.
mm-hmm.
What I've done is I've converted SWE to millimeters and density to millimeters, and then I divide millimeters by millimeters, and then I just have a fraction.
I see.
40, it's a percentage, like 40% density, 20% density.
Gotcha. Okay,
Yeah,
that's done.
it's a good question. Mm-hmm.
Yeah, I
My
just wasn't sure at first because the original equation was reversed, and I was like, that definitely doesn't make sense.
right.
But that's fine. That answers my question. Thank you.
And if you see anything on the homework that looks like it makes no sense, let me know and I will check it and tell everyone else as quickly as I can. Because this is my first time doing the class, I haven't caught my typos yet. So please do help me. My apologies on that one. And yeah, you see density plotted two ways, both unitless as I have, and I'm probably not showing on the screen, I'm showing here. Both unitless here from 20 to 40%, as well as kilograms per meter cubed. And it's just how you normalize the units. All right, so homework 2, and can everyone see homework 2 up on my screen now? Yes, excellent. All right, so homework 2 is an example of homework 2, same as homework 1. I'm going to copy it over. This one is simpler than homework 1. I also find it more intuitive because you don't need to worry as much about what's happening inside the snowpack. So if you go there, also we have the observations, so you can also look at how things compare to observations. So homework 2A and 2B help you set up the exercise. Homework 2C starts with the actual exercise, and I went ahead and already ran it. For all of homework 2C, it's just pushing Shift Enter to run everything and following through the code. So we went ahead and simulated things at Pascal Stork site. And here is our first run. You can see, can everyone see the plot with snow water equivalent? All right, so given what we talked about last week about forests and snow, and given that Pascal Stork's site is at a very warm maritime site, even before we've seen the observations, what do you think of this model run? Yeah, there's too much snow in the forest. It doesn't look like any snow got intercepted. And the snow should last longer in the open, right? At Pascal Stork's site. So now here we actually have some observations. You guys seen the site. And so, yeah, so here's what was observed under the forest in the dashed yellow line, what we modeled under the forest. So again, this is a case of model evaluation. So what might we try tweaking with this? What could we have done wrong? We obviously did something wrong in our model setup. Didn't use sticky snow. You can actually check. You can go back and here says, yep, snow interception has sticky snow. Nope, we did that. Change the canopy. Ava already looked at the homework, I think. Yep, that's what we're going to try is change the canopy long wave, change the canopy wind. So Bart actually went, and so this was what we talked about last time as well, is that if you look at the wind forcing, the wind measured in the clearing site we expect to be low because it's sheltered from the forest, but SUMA is expecting that there's a wind above the canopy. So we actually have to change the observations of the wind speed to be true for above the canopy. So this walks you through how to multiply it by 1.6, which is basically logarithmic scaling up to a height above our canopy. Then we have higher wind speed above the forest. It then will rescale down to lower wind speed within the forest. And then if we run that again through our model, it's still not perfect, but it looks a lot better. So you can play with other things. The only thing required for your homework is homework D talks about changing the long wave simulations. And it will walk you through how to do the Anderson scheme and the observations. Your job for the homework is to choose your choice of two others here. You can pick Prada, you can pick the Tennessee Valley Authority, you can pick Satterland, and then you can pick Dokia either with or without I think Dokia has the cloud correction. So you can have one with the cloud correction. The other ones just assume clear skies. They don't actually parameterize clouds. So you can pick two of these, where the Dokia one, I believe, is the only one that includes a cloud correction, and then see how that changes both snow in the open and under the forest. Then exercise 2E talks about other things you can do. That's only if you're interested and want to do it for your final project. It's not required by Friday. So really the only thing that you need to do is first make sure you run through everything through 2C, and then 2D is go ahead and copy it. Is basically copy the procedure that's demoed for the Anderson with two other long wave schemes. And then for this, you will notice more immediate impacts in the both comparing the long wave you get and in comparing the snow values. So you don't need to spend too much time looking at all the energy fluxes unless you're interested. And then you definitely can plot all the energy fluxes, the interception, as much as you want, but you can get the main answers by simply plotting SWE. And it's only 1 year, so it should be a much more straightforward analysis than the first one. Any questions on the homework? Okay. So, all right.
Actually, I have a question on part D of the homework. I was trying to adjust the long wave for the Dokia estimation, and I was getting an error message saying that I didn't define shortwave or the cloud correction. I tried running the code farther up in the notebook a few times and substituting different pieces from there, and just couldn't quite get it to work. So I was wondering how we define the cloud cover or the shortwave for the Dokia scheme.
So you can see on my screen, we've got the cloud correction. Shortwave may not be. I will check on it. So it didn't work. If you have the error message and can either post, if you have a copy of your error message, can post it. I can look into it.
Yeah, I actually created a discussion late last night, and it's got a picture of my error message and a copy of my notebook, or a link to a copy of my notebook in it.
Okay, great. I will look into that.
Hey, Jessica, this is Tim.
Thank you.
I got the same error, but I think what I did, they have shortwave as a variable in the NCF file, just like air temp. So what I did was just run the NCF dot shortwave or whatever that, I don't remember the variable name. It's like SW something. So I could post that in the discussion, but
that'd be great. If you have a work on it, that would be awesome. Thank you.
Yeah, that'd be super cool. Thank you.
I think I actually ran the first two and said, okay, it works, and didn't run that one. But yeah, please, yeah, let me know anything you find that these are hot off the press, so typos are likely exist. Okay, back to, all right, anything else? All right. Okay, so we went through, just in our examples with both homework 1 and homework 2, a fair bit of model evaluation. What we are always doing every time we run a model is trying to figure out whether it makes sense, and if it's wrong, why is it wrong, and how can we fix it. So as I said with the with what I did with the first homework is, before you decide how many plots to make, are you getting down a rabbit hole of details? What are your modeling objectives? And this is Calvin and Hobbes cartoon that I slightly modified, where Hobbes asks, how are you doing on your modeling objectives? And Calvin says, I didn't make any. See, in order to improve, one must have some idea of what's good, and that implies certain values. But as we all know, values are relative, and every system of belief is equally valid, and we need to tolerate diversity. Virtue isn't better than vice, it's just different. And Hobbes says, I don't know if I can tolerate that much tolerance. He says, I refuse to be victimized by notions of virtuous behavior. So Calvin says all the snow models are equally good, and you could argue that. But really, if everything's equally valid, why even bother to evaluate? By the same token, if you want a perfect model in every way, all the time, everywhere, you will never graduate. So you've got to pick some objectives, right? So what are your objectives and why are you doing this? So what I'm going to walk you through here is first, what are some of the data you can bring to bear on those values that your snow model is producing? Some both point and distributed data, and what are the relative usefulness of these data sources at different phases of the snowpack evolution? And then, what are some common metrics for evaluation? What do you calculate? How do you determine whether you have a good snow model? All right, so here, this is, again, we went through the ideal weather station. This is Mark Rowley's slide. And everything here shown in blue are things we can use for model evaluation, right? Part of the reason why the first homework said, plot snow water equivalent, snow depth, and surface temperature, those are the things that we can most readily measure. So we can actually compare each of these with observations. We may also be able to compare, outgoing reflected shortwave or long wave. One thing to be aware of with the outgoing shortwave is that these shortwave radiometers, most of them, even if you have one pointed down, it has a hemispherical field of view, which means it's supposed to be going out 180 degrees. So it is likely not only to be seeing the snow, it's likely also to be seeing some tower, some trees, something else. There are certain sites where they raise and lower this so it stays the ideal height above the snow surface. But it's very tricky to do. So I would just, in general, rule of thumb, be skeptical of any observations of outgoing shortwave radiation. Other things you might have a snow lysimeter. This is what Pascal Stork had at his site. It may weigh the snow, or you can collect all the snow melt into a tipping bucket and measure the melt rates out of the bottom. You may have snow pit measurements of with a density and temperature profile, and you may have, particularly if you work like near a ski resort or by avalanche patrol, 24-hour new snow accumulation on a board, which definitely has depth and often also would have density, where they move it each day, so you just get new snow accumulation each day on top of the snowpack. You might have some manual snow surveys from the National Resource Conservation Service, or you might have, a field campaign with lots of students or people going out measuring lots of snow depth or snow water equivalent. You might have time-lapse photographs. Here are pictures from a camera of Tuolumne Meadows looking at the snow melt. You might have an array of snow temperatures through the winter. This you actually could plot via our layer scheme. This is an array that Mike Dettinger and his daughter Julia, who's now much more grown up, plotted at the Dana Meadows. This one's from Gin Flat. There's also one in Dana Meadows in Yosemite National Park where they just put temperature sensors on a pole and let snow accumulate around them. And then they worked pretty well until the snow started melting. And then you can see that actually holes started melting around them. And so there were air temperatures much warmer than 0 being measured. But during the winter, they measured cold temperatures pretty well. You might have the ideal experimental watershed. So this is where we were modeling Reynolds Mountain East within the Reynolds Creek CZO. They have many met stations, soil measurements, snow courses, and weirs for stream flow. So you could compare your snow model at many different points and also compare how your snow model integrated and gave you outflow in the stream. For distributed studies, you might have stream flow, where you have your model and measured stream flow, which if it's a snowmelt dominated watershed, likely bears on how well you modeled the snow. You might have satellite or aerial remote sensing of fractional snow covered area, the date when snow disappeared. Here's pictures from MODIS, from ETM, that's Landsat, and from ASTER. It's just 3 different satellites that have snow covered area. And so you grab everything you can get. Model runs, you're really only limited by your time and perhaps your computer resources. Observations, you generally want to grab everyone you can, and then you still feel you don't have enough. So what are the most useful ones for different phases? So the next thing in evaluation is, it's just like we found that plotting all of our model results at once weren't so helpful. Often trying to evaluate all your model results at once is similarly not so insightful beyond just catching a really major egregious error. So I like to think about the snowpack in 3 main phases, where the first part is snow accumulation. And this is really going to depend on precipitation and snow drifting. Are you modeling precipitation right? And as I showed you when we talked about met forcing, most problems originate from having the wrong precipitation. To assess this, you need an accurate measure of snow depth or snow water equivalent. And what we've got here is showing snow depth, and then the colors are showing the evolution of snow density, where green is higher density. In the middle of the winter, the snow often, there's some period where it's not changing much, but you will have an evolution of snow temperature, and that's going to determine whether or not and how much midwinter melt might occur. The snow density and the liquid water content can change quite a bit during this period. And this is often the trickiest period for model evaluation. During the melt season, again, the depth and the snow water equivalent are changing. And towards the end, the snow covered area becomes very important. And this is when we can start really using spatial metrics to assess our snow model. It's at the very end of the melt season. Here again is a picture, snow depth, and here colors are just representing snow temperature, where blue is colder, orange is warmer conceptually. Snow temperature represents the energy balance at times when snow water equivalent and depth changes are not evident. And so this is a good metric to check this time, even though, as you notice from the multi-layer simulation, it's not the easiest thing to do. So, okay, we know how to make plots, we can get all of this data. What metrics should you be calculating? What should you report? And if you get a number from these metrics, what does it mean? So one of the papers you have an example of is Richard Ezery's 2013 paper about 201 snow models. And he has our most common metrics I showed you on a good met station, right? He has a measure of snow mass or snow water equivalent, snow depth, snow surface temperature, and albedo, even though please recognize that measurements of albedo are hard to take, so take that with a grain of salt. And then he determined the best models by minimizing the root mean squared error, or RMSE, for each of these individual variables, and then used a weighted cost function of the 4 variables. So he weighted your average root mean squared error, by the size of things across these 4 variables. Root mean squared error is a popular metric. It was used by Slater and Clark, 2006, Andreas et al., 2006, and Liston and Heimstra to evaluate various data assimilation schemes. You will see that many times. Christy Franz et al., 2008, was evaluating 2 snow models. These are simple ones, right? We talked about the Snow 17 model. And she calculated a lot of metrics. She calculated the mean error, or ME, and here's the formula for that. The root mean squared error, that's the one we just saw in Richard Ezery's paper. The Nash-Sutcliffe efficiency, which is this formula. The percent bias, how different is something divided by what the variable is. And a correlation coefficient, how well was her snowpack and discharge correlated. James and Burgess in 1982 were looking at ways to look for errors, and they advocated very strongly, instead of just calculating metrics, as you see, we've got a long list of metrics and their definitions that you could calculate, to always make many, many plots and many visual inspections to check for various model biases. For example, you could see that the higher magnitudes have problems in the upper left one, that here and right below that the higher magnitudes are simulated too high, the lower magnitudes are simulated too low. So again, just making scatter plots of your observations versus your errors before you bother to calculate things. The upper right-hand corner is a systematic bias, and then your lower right-hand corner shows no systematic error and that everything is working. It's the case of the lower right-hand corner when your root mean squared error actually has the most information. When there are other problems, it tends to be secondary in importance. Other things, this is Mukeshkumar, 2013, was trying to model both snow runoff and the groundwater table in Rails Creek. Again, he made plots of everything. So, here are all of our observations. Here are all of our different model runs, how it simulated everything we have observations. He marked observations that he thought were wrong, but still reported them. So these circles with squares are suspect observations. And then he also calculated the coefficient of determination, which is the square of the correlation coefficient, and the Nash-Sutcliffe efficiency. Other things that people do have calculated, what is the mean difference between relevant variables. You can look at summary variables, particularly if you're doing a lot of simulation. So for example, you might look at, what are differences in the centroid of the annual snow water equivalent time series? What's the seasonality of snow accumulation and ablation? Are you switching between the accumulation ablation seasons properly? You might just calculate metrics only for the maximum SWE. How well does your model get the maximum SWE? You can look at snow season length. This is a good one to compare with satellite imagery, right? How well do you model the number of days when snow is on the ground? The runoff ratio, how well do you get the ratio of runoff to precipitation? And then you can do the centroid of the annual runoff time series. So what's the timing of the annual peak runoff, which is often related to the timing of snow melt. So just to summarize, that was a very quick run through. You're not required to do any of these for your homework. You might choose to do some of them. Really, I want you just to have a bag full of tricks as you go forward of what things can you calculate and report. How do you fit them? There's a lot of goodness of fit variables which are really for any time series pair you can set up. Correlation is going to tell you how well both go up and down at the same time. The magnitude differences will be minimized in this report. So if you think you might have a bias, but you systematically are making things go up and down at the right time, you'll have a decent correlation. Root mean squared error tends to emphasize outliers. You'll get more error if you have more outlier points. Choosing instead to do the mean average error will put less emphasis on the outliers. So again, depending on your depending on what your focus is, if you're really concerned about extreme events, you probably want a metric that emphasizes the outliers. If you're less concerned with extreme events or think your measurements are not good in extreme events, then you probably want the mean average error. Bias is important, particularly for something that you're going to integrate, as in snow all over a watershed for water resources, right? A bias is going to tell you you have too much or too little snow, whereas random error is less likely to if you integrate it across space. Nash-Sutcliffe efficiency is typically used only when you're comparing with stream flow. It tells you how well do you do compared to only forecasting the mean. So if you were just to forecast mean runoff, how much better do you get than that? So 0 means that you do about the same as forecasting the mean. Some people will report negative Nash-Sutcliffe efficiency. That means that your model's pretty terrible and you would be better off just assuming you got mean stream flow every year and you shouldn't model at all. One gives you perfect. Other things I just showed you were just doing metrics of characteristic signatures, and you can perform the goodness of fit variables for the characteristic signatures that I just went through. So here are some, I guess, another example from Nick Wayans' 2013 paper, where he was modeling, trying to look at things spatially. He had some observations of snow at the blue dots here where they're labeled. This is where he measured peak SWE. He's trying to see, did he capture how peak SWE increased with elevation? And he had 2 different forcing data sets. And you could see that, that the black one seemed to model peak SWE better than the red one. Total precipitation actually seemed rather comparable, but there were only 3 measurements between them. And temperature was different, but again, with only 3 measurements of temperature, kind of hard to say which would be better. Then looked at 2 locations with observations with the observed snow water equivalent for 2 sites. One that had more total snow water equivalent, one with more midwinter melt. And then here was the first model, which actually was matching SWE better, but maybe it was matching SWE for the wrong reasons, right? It accumulated too much and melted too much. This is a common issue in that 2 wrongs can make a right later in snow modeling. And so it looked pretty good out here, but something wrong happened in here. Whereas by comparison, the other one, which looked much worse in terms of getting peak SWE, actually got accumulation right here, but just melted things similar to this one. But here the wrongs stayed wrong. So it's complicated. And it's hard, the more you stare at it, to declare which one was really a better selection. So the more plots you can make, the more time you can dedicate to evaluation, the better. See, these 2 ended up with a similar meltout pattern, and so the one that actually matched better had too much accumulation. All right, so I wanted to switch now to show you some of what Drew Slater shared just in terms of thinking about these metrics for evaluation. And this was a talk he put together for the 2014 snow modeling class that we taught before. And you read Drew's paper. Sadly, Drew is not with us anymore, so we can't have Drew give the presentation. But I'm going to show you his thoughts, because I think he had some really great slides on what you should think about. Before I transition there, are there any questions so far? And please, if you are, if you unmute your mic, if it's not too hard, I think it's almost quicker than typing. Any questions? Okay, well, feel free to interrupt me if you're just having mic difficulties and wanted to say something. Just go ahead and stop. Okay, so so root mean squared error is probably the most common evaluation metric you will see. And so this was just simulations done with a very simple snow model. So it's similar to Snow 17 that was run at 599 snow-till stations across the entire Western US. And this is just a distribution of the ranked root mean squared error across all of those sites, all 599 sites shown here. Okay, so what does that mean? Well, clearly we have some over here that are just absolutely terrible, right? So our model worked horribly there. Maybe. Next choice we can make is we could only look at our observations when SWE is greater than 0. So one thing to be aware of, particularly if you're reviewing papers, is that if you include times that your model says there are 0 snow and there are 0 snow in the observations, you generally get a better number for your metric. Most of the summer, we'll all agree that most places there's no snow. So it might be more fair to just calculate times when you think there should be snow. But that's subjective. We get the same overall shape here. Now, what if we plotted those root mean squared error versus the mean annual maximum snow water equivalent? So what we see now is that places that have more total snow water equivalent also have more total air, right? So you will have smaller absolute numbers at places with smaller SWE, even though you might be off by a factor of 2. So are you, comparing the straight root mean squared error might not be fair if one site has, 5 times, or here, 3 times as much snow as another site. Now, the next thing you can do is you can normalize the root mean squared error by that, right? So here we see, okay, it looks like you have, that you just want a fraction, right? How far off is it as a fraction of our total SWE? If you do that, you will tend to emphasize errors at sites that have the smallest amount of SWE, right? If you divide by a small number, you make your error look larger. So it's often worth considering both of these metrics, both the absolute root mean squared error as well as a normalized root mean squared error. You can also see that above a certain value that we no longer see certain sites having huge amounts of error, that most of these now have roughly the same percentage error, somewhere between 5% and 25%. Now you could plot this normalized root mean squared error, so you divide it by the maximum, by the coefficient of variation of the mean annual SWE. So the coefficient of variation is the standard deviation divided by the mean. And here you can actually see that this kind of makes sense, that the model is having more trouble representing places that had a really high standard deviation in the amount of snow water equivalent they have. So if there's a lot of natural variability just in the observations, your model might also have more trouble, and you might think that you're willing to accept that it's a harder challenge. So what people often do is, make time series plots and plot as many metrics as seem relevant to you and consider them all together. And again, the coefficient of variation is the standard deviation divided by the mean. We just went through the root mean squared error, the normalized root mean squared error, that's divided by mean SWE, the maximum SWE, and then our coefficient of variation. So we've got Pole Creek up on the top, and it's the first line of values here, and White Horse Lake down on the bottom with the second lines of values here. So of these two sites, which one, you can write Pole Creek or White Horse Lake, do you think is modeled better? Looks like everyone's voting for Pole Creek. It has the smallest normalized root mean squared error. It's actually also has less variability from year to year, so it has a smaller coefficient of variation. It's a subjective decision. There isn't a right answer. Pole Creek is generally a much easier simulation to do. For this model to match Whitehorse Lake as well as it does, I'm actually very impressed with the model, because if you look at the coefficient of variation, here the normalized root mean squared error is pretty low compared to the coefficient of variation. So I would say that, yes, overall it's doing better at Pole Creek. Pole Creek's an easier site. Given the challenge of Whitehorse Lake, it's actually doing quite well there for what it was set up against. Okay, all right, so here is a time series, snow water equivalent, of observations at a site. This is one of the SNOTEL sites labeled Divide. It's at 2,377 meters. And here's model A. And it got a root mean squared error of 37 millimeters, a Nash Sutcliffe efficiency of 0.9, which again, it ranges from negative number being bad to 1 being perfect, and a correlation of 0.95. So before I show you what Model A does, how complicated do you think Model A is just based on these metrics? It's hard to tell from the metrics, right? Some of you say complicated, some say maybe simple, relatively simple. Model A assumes that the average snowpack repeats every single year. So Model A is this green line. You just take the average of the whole time series and presumes that the snow accumulates and melts exactly the same. It's a simple looking site. That's a good observation, right? It actually does do about the same thing every year. It doesn't look like a hard site to model. So you just presume that whatever happened last year happens this year, whatever happened on average in the past, you do pretty darn good. So now if you're going to bother to use a more complicated model for this site, you'd better hope you can beat this, right? That if it's better just to go with the average snowpack, then your model you're bringing to the site doesn't add much other than a headache, right? Okay, here's model B. So that's the blue line. This is the model. And it does. You look at the plot, it actually does match the observations better. But then you look at the numbers, and they're not that much better, right? There is improvement, and you see that in the picture, but it's not huge. You can also get another site. We did the same thing with the place SNOTEL called Tyser Basin, and in this case, Model A is the average, the green line, just to mean average every year. Model B was running your temperature index snow model, and it actually did worse in all metrics. So guessing the average actually does better than the model. This type of analysis is a good way to normalize what we were subjectively doing for the prior one, where I looked at a really hard site to model and a really easy site to model. I said, well, the model's doing better at the easy site, and here the model is not actually offering us more information than the mean. And Scout asks, which metric is the most important or telling, and does it change for each site? My opinion on this is that making as many plots as you possibly can, the human eye and your ability to visually assess things is by far the best. That's the one thing I would not give up, is we are, especially if you give multiple choices of squinting at a lot of things, we're pretty good at seeing what looks right. So I would do plots first. Root mean squared error seems to be the most popular, but that said, as you could see from the example from Nick Wayans' paper, that you could have two errors cancel each other out really well and get a really good metric when maybe you shouldn't. So in addition to thinking about how well your model does versus just an average or a simpler model, you want to think about what are your observations. You know, if you all of us have gone out and looked at snow at some point, looked at pictures of snow, you know, what does an observation mean? And if you are not modeling at the perfect snow measurement site where you have all of the local meteorology exactly where you have your observation, you know, you could almost run your model simulation and then go out on this landscape and find the point that you match perfectly, right? If you have a big grid cell, you probably match some snow depth somewhere out here. It's a difficult question, and again, you have to think about your objectives. You know, if you want the mean value out there, you need to think about what will give you the mean value. This is a picture of a grid. So you're trying to model this grid cell, and what you see here is an aerial photograph of where people have walked in transects, making snow depth measurements everywhere along this grid. And then little circles are where people have walked in circles, making millions of detailed snow measurements in one circle. And this is Matthew Sturm's site. And again, all of those measurements together went into, did the model get snow right out here? And here is a map of where the snow was. It's upside down to match the picture. And there's more snow on this side. This is what all of these measurements told you in terms of snow depth, where red is 100 centimeters upside down, and the most is over here on the screen. Also, satellite data, you download it and you get maps of snow-covered area. What does that really mean? So this is a picture of Martin sitting in the American River Basin. This is the North Fork American River Basin, looking out with a map and saying, well, looking at snow, looking at trees and saying, well, what snow do we really see, right? Satellites don't see snow under trees. So how do you interpret that? Also, is your observation a model variable? What does that mean? Again, we talked a bit about sensible and latent heat flux. As you read in Drew's paper, the different land surface schemes, will output, an effective heat flux that includes both the snow and the soil. And if there's patchy snow, it's all lumped together. Other ones will do subgrid tiles, where they might output one specifically for the snow, one specifically for two vegetation types. So you need to think about what is the footprint of your model grid cell, and if it's large, how are parts of that model footprint aggregated? How does that aggregation relate to your measurement? If you have a flux measurement, what is it aggregating over? If you have a satellite measurement, what is the spatial scale of what it's looking at? And are what you're looking at actually the same as your model variable? What's the scale of the photo? The one back here, it's pretty big. In all honesty, I was out there at the site and we used a snowmobile. These were snowmobile tracks, and you went along with the snowmobile and took the depth measurements along the side. I believe it's a kilometer by kilometer, and they're 10 meter by 10 meter, and all the little grids, I think, are the scale of the photo. But if you look up this, we'll tell you for sure exactly what it is. That's me remembering from going out there. I'd have to look in the paper for exactly. All right. The other question that comes up quite a bit in snow modeling are, particularly if you're trying to model over large spatial scales and you have a footprint that's too large for a snow till site, you may want to go get a nice snow product, right? Over what's the basin mean snow mass balance? You could go, look up something for an entire basin and say, well, this is average SWE. What is this, and does it make sense? And so if you look at what products are available, the thing to realize with these products is that they are all various forms of models as well. So this is a picture looking at if you wanted to do global or northern hemisphere extent snow, and you wanted to know if your model looked reasonable, you could go get any of these 12 products off the internet and you could make these plots. These are the mean March snow water equivalent for 2000 to 2009 across all of these plots. And what is the first thing that comes to mind when you look at this? Well, these are incredibly variable. Yeah, Greenland doesn't have snow in some. The variability is huge. Measurements are really difficult. Modeling is very difficult. There's a lot of places where truth is really elusive. And so it's really hard. And if you are doing a simulation where you grab a product and compare with your simulation and don't actually understand all the caveats of that as well, you just end up adding to community confusion. Also, Grace thinks there's snow everywhere, right? Because it's actually just measuring groundwater as well. This is just how well all of these products correlate spatially with everything else. And AMSRE and SSMI match the least with everything else. Again, matching other things doesn't necessarily mean you're right, but it can give you an idea of which products are more outliers from each other. Grace is also pretty different from most things. All right. Other things you want to think about in terms of, again, what you're trying to do. So if you're running an atmospheric model and you're trying to figure out air temperature, soil temperature relationships, you're interested in permafrost, you want to think about how is snow implemented in your model relative to the soil, right? That you can get from an implicit model where snow is just part of the soil, it just makes it have higher albedo sometimes. You get a much lower effect than if you actually have a multi-layer snowpack that you put on top of the soil. So again, if you are interested in variables beyond just how much snow is on the ground, as we learned from our multi-layer modeling study, you often need to be more cognizant of more complicated aspects of the model you're choosing. Then model diagnosis. Okay, we want to calibrate our model, and I'm going to do this fairly briefly here. So here's our first run. And this is a simple, think Snow 17 simple snow model with accumulation and melt processes. So it's not as complicated as SUMA. What's the first, and what we've got here is we've calculated the root mean squared error, the accumulation season root mean squared error, the ablation season root mean squared error, the error in the maximum SWE, and the average melt rate. So what's the first thing you would try to fix about this snow model? Yeah, everybody says, fix the bias, fix the accumulation, right? So the first thing is that probably the precip input is wrong and we need to multiply it by something, because in all these different years, we don't have enough snow water equivalent, except that one, we did pretty good in water year 08. And in general, our accumulation root mean squared error is bigger than our ablation root mean squared error. So we're having problems with our accumulation season. Okay, so we fixed the accumulation. Now we've got this run right here. Again, same calculation. So what's the next thing you would fix? The melt rate. How should we change the melt rate? Do we want it to melt faster or slower? Yeah, and in general, and in some years are different, but in general, our model is melting out too fast. We want it to melt slower. So This is a very simple model in this case, so it's a temperature index model. So we would just change the temperature multiplier, the rate per temperature. If we were looking at this in a more complicated model like SUMA, oh, our observations red. Yeah, that's a good point. So if observations are red, then it's not slower. We're all reading it wrong. So if observations are red, it's melting too fast. Yes, so then we want it to melt slow. No, our model, we can't change our observations. I'm sorry, guys, it's been a long day. So you want your model to melt faster. Yep, everyone said slower. I think you were all looking at it, right? So make the model melt faster so the blue line matches the red line, right? Good catch. Yes, thank you. We're just going to go with the popular vote here. Yes. All right, so our model needs to melt faster. So again, we can tweak our melt rate. If it was more complicated, we could change our radiation. We might want to look at our long wave parameterization. And so that's something you can evaluate with homework too. And I find that that's a little bit simpler than trying to figure out the internal physics of a snow model. So if we fix the melt, now the lines match up beautifully. Yes, and you can see that if we go back and forth, it read our observations and we now made it melt faster. Even though, did we make it melt faster? Now have a slower melt rate. Maybe that was our melt rate error. Apologies, I'll look at this again. Then, and the spirit of Matthew Sturm, these are Drew's suggestions of, does your model do this? So this is looking at the Arctic snowpack, and this is where the shrubs are under the snowpack. So this is, a wrench centimeter scale here, and this is, what's happening is that you've got really thin snowpacks, you've got the shrubbery underneath the snow, melting it. All right. Any questions? All right. So the final thing in model evaluation that I want to convey is just to think that you are constantly working as a detective, that just calculating root mean squared error and plotting it is a step, but it's definitely not getting you there all the way. So here is our quiz of the week, beyond what were the snowmobiles, is what is shown here. And the hint is that this is quite hard and may not be strictly about snow. I don't know the answer either. But if you know the answer, we can send it back to Matthew Sturm. He stumps me repeatedly. It's like frozen waves, maybe? Is it like, might be. I was thinking it was a frozen cabbage, but I'm really not sure. But if we can pool our best guesses and vote on them, send it back. Yeah, maybe it is frozen waves. Probably somewhere in Alaska. Okay. So in being a detective, when you have eliminated the impossible, whatever remains, however improbable, must be the truth. In the interest of time, I'm not going to go through the first one here. I'm going to go through it very, very quickly. If you're interested, I ended up presenting this at the 2014 Snow Modeling School, and the students liked it so much they said I had to write it in a paper. So it's in the diagnosis of insidious data disasters. And this is a problem in Yosemite where we could not model stream flow. Spent, I don't know, more than 5 years of my life trying to figure out how to model stream flow. I will go ahead and post this. The answer is there's a tree growing in the snow pillow. So the short version is go visit your site. When in doubt, go and look at it. And when you pull a tree out, it weighs too much. I'm going to jump ahead. I think this one, because we are talking about long wave radiation. So here was another problem. So we were running the SUMA model here, at the Snoqualmie Pass measurement site. This is a slide from Nick Wayans, and this was our observed snow surface temperature. He was running with the Jordan method with as many layers as he could get, and just kept modeling with the observed long wave that we could not get the temperature cold enough at night. And so he tried changing all kinds of parameters in the model. He tried all the different thermal conductivity options. He tried different ranges in the conductivity options. It had a pretty small effect. It just didn't do much whatsoever. We just couldn't get our snowpack cold enough. We tried some different turbulence flux options. So we tried Standard, Lewis, and Mart. Carl hadn't yet told us that they were all pretty crappy, but they didn't do much anyway. Then we said, well, you know, what else could be happening, right? So we look, this is the middle of the night, right? What controls? We've got the change in the surface temperature with unit time is related to the incoming long wave radiation, the outgoing long radiation. It's nighttime, there's no shortwave radiation. It's not raining or snowing. We looked at dates with no wind, nothing was going on there. And so, you know, maybe our observed long wave could be wrong. When nothing else was happening, might that be our explanation? So we started writing the radiation experts. So we wrote to people at Kip and Zone and given us our radiometer. We said, maybe your calibration wasn't correct. And they wrote back and said, by the way, agreement or not with the model does not seem to me to be a good way to choose the correctness of a measurement. Told us to go away. But we just couldn't come up with any other ideas. Like, what else could we tweak here? We're not going to change the specific heat capacity. So we went and took it to a black body and tried calibrating it. And under the calibration, the basically what a long wave sensor gives you is it measures voltage, right? So you have millivolts and you multiply it by something that comes with the sensor when you buy it from the factory, and they give you a number. So you multiply it by, they told us to multiply it by 73. That's what we were doing. And when we calibrated it, we got a new multiplier of 123. Said, So we called them up, we told them, and their engineer said, well, please remember that the purgeometer are calibrated against a hot plate and not outdoors, and a hot plate does not simulate the sky properly. So a shaded and ventilated CGR4 is required for accurate data. The manual contains individual specs of the zero offset and the daily uncertainty, which should be 10%. So they told us we shouldn't have been using their instrument in the first place. Then we got another email from Campbell Scientific that said, we recently discovered the inaccuracy of all the programming examples in the manual, as well as the inaccuracy of all the programs created by the shortcut build that apply incorrect multipliers to the sensors being measured and give erroneous values. So we were not too wrong with our detective work. 1 month later, Campbell released a new radiometer value and said it should have been 148. We then corrected the long wave, and here's with the original, and here's the corrected long wave observations, and here's our ability to match the model on those nights. We did have the incorrect long wave radiation. It was worth asking questions. And I will stop there. And let me know questions about homework 2 as you find them. I will try to fix typos as quickly as I can. Thank you.